Welcome. This web lecture is on how to create a concept map. This is an effective way to learn that not only may help you remember what terms mean, but their context, their relationship to other terms so that you can apply them in a variety of contexts. This not only is an important aspect of knowledge, but it is a way of burying things in your memory so that they stay there, not just through an exam, but after the course and well into your working life. Concept maps that you've seen before, but likely not made very often, convey a variety of sorts of relationships, and the best ones will identify the types of links, from inclusion to characteristics, actions or processes, temporal relationships, and similarity. So if we have matter with 3 states of water, you know what those different states are. They differ in part by temperature. Changes occur in temperature in part due to pressure or along with changes in pressure. It's a physical change, although the chemical structure remains the same. So this concept map here captures many of these relationships with arrows and descriptions along the arrows. So here's another sample concept map. This is important perhaps for evolution, where there are facts that we can observe. These facts can lead to hypotheses that we build into theories and laws. So there are observations, and for well on 200 years, there have been a number of observations that have prompted biologists to suspect evolution. These facts get put into proposed hypotheses, and as more facts are generated, we can test those hypotheses. If hypotheses get consistent results, and there are many of them, they may lead to a new theory. And the theory makes predictions that may generate new hypotheses. That theory can be built into a law, such as a mathematical relationship between factors. So in a STEM field, this is how we might describe a law. All observations of a theory and a law have to be consistent with the facts, and if they're not, they need to be revised. This is how a number of scientific theories and laws, from physics to biology, have been built. All right, so this is a fairly simple one, but it's important for how we do science. This concept map of the relationship of facts, hypotheses, theories, and laws depicts fundamental components of how the scientific process works. We'll walk you through another more sophisticated one. What are the conditions for life on Earth? You've got a planet surrounded by space, may or may not have an atmosphere with different things in it. So some of the conditions that we think are essential for life are moderate temperature and liquid water, at least life as we know it. So lower temperatures mean more water is liquid than gas. If we go to the planet Venus in our own solar system, its higher temperatures mean most of the water, if it's there, is in a gaseous form. And although there's limited amounts of it, if any, on Mars, what water there is not at a moderate temperature, it's a cold temperature, and it happens to be frozen, as it is in more distant parts of our solar system. All right, so what gives a moderate temperature? Well, third planet from the sun, but also if we look through the several billion-year history of our solar system, there's less bombardment by asteroids. Has given Earth time to cool down. Reduction of CO2 levels leads to increases in vapor. So we can use our understanding of the atmosphere to see where carbon dioxide and carbonic acid are in the oceans, in the crust, and in the atmosphere. They have important roles, not only in facilitating life, but many of these relationships remain very important for understanding what will happen as consequences of global climate change. All right, so we can build on the start of a simple concept map by adding more. Atmospheric CO2 combining with water to form carbonic acid, the reaction of that with rocks, and give bicarbonate and calcium, etc., etc. So building on. Another important condition for life on Earth is the formation of organic molecules. How did these form? We've got different conditions that we can get in the atmosphere. There's a set of very famous experiments from the early 1950s performed by Miller and Urey where they created conditions that they thought were consistent with a reducing atmosphere of early Earth, 3.5–4 billion years ago, that would have had these molecules in it, and they put them together at high heat and generated many of the organic molecules that are part of life. Perhaps some of these came from space, sort of drifted into the Earth's early atmosphere, and we can find some evidence of organic molecules in meteorites. And as we have the technology to sample more of them, we may find more and more in space being generated. Okay. Another important condition for life on Earth is the origin of metabolic pathways. Were the early organisms autotrophic? Did they build organic molecules from inorganic ones? Or were they heterotrophic? Did they take them up from around them? These are some of the questions that we may need to answer. One of the hypotheses for the origin of the material of heredity, nucleic acids, is that although most life now uses DNA as its hereditary material, RNA, which also has some autocatalytic properties, may have been the original hereditary material because it can act as an enzyme before some amino acids existed. This is the realm of hypothesis, but it's an important component of understanding the origin of life. All right, where did the cell membrane come from? This is important for protecting life, defining a coherent living organism that's capable of replicating. Important parts of the definition of living things. Okay, so maybe cell membranes form from fat. They do form from fatty acids. It could have formed layers, although then how were they replicated? These are important questions to which, to be honest, we don't know the answer. All right, so you see here, this concept map has encompassed a lot of important information from disparate sources, from experiments like those of Miller and Urey, to observations in geology and planetary physics, to our growing evidence of how viruses and some bacteria behave. Lots of different pieces of facts put together to build knowledge. Now, I should say, the origin of life is a fascinating question. This is a course, however, in evolutionary biology, and for the most part, we will not address this question. It's a fascinating question, but it's really outside of the realm of modern evolutionary biology. It's something about which, frankly, we know very little. Much of it is lost to the last several billion years on Earth, where life and planetary processes, erosion, tectonic uplift, other forces have destroyed most of the evidence of early life on Earth. And life itself has drastically changed the way Earth behaves. It's put oxygen into the atmosphere. It's colonized most of the terrestrial surfaces, when we have lots of evidence suggesting it originated in the sea. These are interesting questions, but to be honest, they're simply not the subject of this course. Nonetheless, for the activity of building a concept map, this is how one's done. So I'm going to leave you, you can stop on this screen to look at how this looks. And then I'm going to show you the next two screens where each of these connections that I've described a little bit is labeled. All right, So I'll give you a second. If you need to, you can freeze the screen so you can read these at your leisure, as I have only explained them briefly. And here's the rest of the list of connections in this concept map. This is an activity we're going to do a fair amount this semester. It's the first time I've done it in this course, but there's lots of evidence to suggest it should be a very effective learning activity so that you convert your knowledge of terms, your ability to define them, into connected pieces that you can use and apply. Looking forward to seeing you in class.